Welcome to CW 11.4. This video is just in case that I'm unable to be in class because of the COVID shot. So hopefully I'm in class, but if not, please follow along and spend the period working through these questions. So the first one is a warm-up. Now that we've done quite a bit of work on parabolas and ellipses, we're going to talk about how to make the distinction between the two. So number one, identify the conic as a parabola or an ellipse. If it is neither, write none. If it is a parabola or ellipse, find the value of A or P. So A in terms of the major axis piece of your ellipse, and then P is obviously relating towards parabolas. So the P in parabola formula. So for the first one, we should immediately notice that there are squares here, and a plus and 16. So just to make it more clear, we can divide everything by 16 because I want it to equal 1. So now I have x plus 5 squared over 4 plus y minus 1.5 squared over 16 should equal 1. And now it's quite clear this is an ellipse. Now I can see that the bigger number is under your y, which means you're dealing with the football form, which means that is your a squared. Therefore, a must be 4. So we'll circle that, write 4. The next one, so I can see there's only 1 squared, so this is clearly a parabola. So I can just note parabola there. Y squared minus 6y. Let's move the 4x over. 4x minus 7. Now let's complete the square. So add 9 to both sides. For that, I have y minus 3 squared. That's equal to 4x plus 2. And then I'm going to factor out that 4. And now that I factor that 4 out, I can see everything pretty clearly. That 4 must be equal to 4p, so p must be equal to 1. All right, so first question done. Next one, we're going to write the equation for the ellipse. So first, notice here's our center. So the center must be 2, negative 4. Whenever I do these, I want to start with the center because you're going to put those pieces in. Y plus 4 squared equals 1. Now the only issue is, well, what is this piece and what is that piece? The simplest way to look at it is really look at your ellipse here, and in the x direction, notice how this is 2, which means this relates directly to what's under right here. So you square it, and that's 4. And then I can see in the y direction, that's 3. So we square it, that must be 9. So I can see that this must be a squared, that must be b squared, and that's pretty much it. So first 2 questions done. Now let's get to the harder ones. So first one, so all these questions at this point are going to relate to ellipses and how they work. So it's kind of a cool question. It's about a whispering gallery. It says Jim, standing at one focus of a whispering gallery, is 6 feet from the nearest wall. His friend is standing at the other focus 100 feet away. What is the length of this whispering gallery? How high is it, or how high is its elliptical ceiling at the center? So this is a thing that actually happens if you've ever been to like a science center, or really any type of dome where it creates like a sphere or an ellipse. It does create like a weird effect with sound traveling. So what we're going to do is we'll make some gallery like that. put the two focus points. And this happens in life, where like if you were to stand in either of these places, all the sound would ricochet off of the ceiling and actually hit you, and you'd hear like everyone's conversation. It's actually quite strange. The question is ultimately, what is the length of the whispering gallery, and how high is it at its center? So to highlight everything, we're looking for this distance. We're also looking for this distance. Okay, so let's start working. We know that Jim is standing at one focus 6 feet from the wall. So this is the wall. Let's say Jim's standing right there. So I know this distance must be 6. And then his friend is 100 feet away. So that's going to mean if this is Jim, his friend is 100 feet from there. So let me get rid of this. So here to here must be 100. So at this point, we can make a couple conclusions. If this is 6, this must also be 6, because everything is symmetrical for an ellipse. And then now this focus point, let's erase the F. That point should be 50, 0, since this is clearly 50 because that's half of 100. Which means this point right here should be 56, 0. So already we can answer one question. The length of the gallery is 112 feet. And that's because if this is 56, the other side should also be 56. All right, so no problem. But now the harder part, how high is it at the ceiling? So to do this, let's make the equation. The way I drew it, the center is right at the origin, which is convenient. So I can just write x squared over something plus y squared over something should equal 1. So in the x direction, this is 56, so this is 56 squared. And the y direction, we'll just call that b squared. All right, so now we got to figure this out. So let's do a couple things. We do know that the distance from the center to the focus is 50. So that would mean c should equal 50. And we also know in ellipses that c squared is equal to a squared minus b squared. So c squared is 50, so plug that in. So 50 squared, that is equal to a squared, which is actually 56 squared, minus b squared. B squared must equal 56 squared minus 50 squared. And at this point, we could use a calculator. I'm going to show you a cool math trick. This is a difference of two squares, so that's 56 plus 50, 56 minus 50. So b squared should equal, that is 106 times 6. So b squared should be 636, which means b is the root of 636. And how high is it? So we can actually use that, root 636, because that would mean the formula is 636 right there. And we can answer the question now. The height of the ceiling at the center is the root of 636 feet. And then we could reduce that, but just to keep it simpler in this chapter, we'll just leave it like that. Okay, next question. So in these problems, we're going to talk about the orbits and basically our galaxy. It says, use the fact that the orbit of a planet about the sun is an ellipse, with the sun at one focus. So this is actually true. A lot of people think that, well, not think, but we know the Earth will orbit the sun, but they don't realize that the sun is not at the center of the orbit. The sun is actually at a focus of the orbit, and we're actually rotating like that. And the center is actually like space. That's actually kind of cool. It's a really interesting use of ellipses in terms of how our galaxy actually functions. So it says the aphelion of a planet is its greatest distance from the sun. So you can see right here, that's the aphelion. So if the sun's here, essentially the focus to the other side. And perihelion is its shortest gap. So like here to here. And then last term, mean distance of a planet from the sun is the length of the semi-major axis. So essentially that's half of the major axis. So effectively that's A. And then here's a picture we'll refer to for everything. So let's try our first question. It says the mean distance of Earth from the sun is 93 million miles. So that's going to be like our A value. So I know that here to here, that's 93. Here to here must also be 93. The aphelion is 94.5. So the aphelion is like the other end to the focus. So 94.5, that means the focus is quite close. This picture is already kind of bad, but that's all right. So the sun is right here, and here to here, that's 94.5. And it says, what is this perihelion? So the perihelion is simply this distance, the sun to the other side. So the calculation is pretty easy. Let's do 186 minus 94.5, and that would be 91.5. So I can fill that 91.5. So we can answer that first question already. The perihelion is 91.5 million miles. Now this is write an equation for the orbit of Earth around the sun. So we'll use our standard equation. X squared plus y squared equals 1. Make our fraction. Make that a little bit nicer. So I already know that in the x direction, this is 93. So that's going to be 93 squared. So that's already pretty good. And then I'm going to put b squared right there. And then, of course, we use our standard formula now. C squared equals a squared plus b squared. So already I can see that if this is the center, and this is 93, this is 94.5, this little piece right here, the distance to the focus of the sun, is 1.5. So that's our C value. So let's come back over here. That's 1.5 squared. That's equal to a squared, which is 93 squared, plus b squared. From here, we just got to solve it. And then you get 92.988 roughly after it's rounded. So I'll make that an approximation. So our equation, we'll make it a little bit rounded. We'll do this, 92.988 squared, which means the orbit is quite close to a circle, because these numbers are obviously very close to each other, but it is in fact elliptical. So this picture that they drew for us here is kind of an exaggeration, so we can see here doing the math that it's much closer to a circle. It's just slightly like an oval. Okay, next one. A planet orbits a star in an elliptical orbit with the star located at one focus. All right, so essentially we're doing the exact same thing now. So I'm going to do a little sketch for us here, something like that. I'll put some generic focus right there. The perihelion of the planet is 5 million miles. So the perihelion is right there, your short leg. And now there's a new word, eccentricity. So in PCH, you'll use that word quite a bit. In 2H, we don't cover it too much. All you really have to know is that the eccentricity of a conic section is this right here. It's a ratio of C to A. So again, we won't use this too much in our class, but when you go to PCH next year, this is a big topic that you'll go into more in depth. But for now, we'll just use it in this question. It says the eccentricity of the orbit is 0.75. Find the aphelion of the planet. So the aphelion is, of course, the long side. So we're looking for that. Okay, so let's write down what we know. Eccentricity, that is the ratio of C to A, and it tells us it's 0.75. So 3 over 4, that's equal to C over A. Now we don't really know C because that's here to here, and then this to here, that's A. So we can make a nice equation because that would mean A should equal C plus 5. And if we know that, we can use the fact with 3 over 4 equals C over A, because this creates, hopefully we all remember the vocab, this is a system. So we're going to plug it in. So 3 over 4 should equal C over C plus 5. So 3C plus 15 should equal 4C. C is equal to 15, which means that A is equal to 20. So to find the aphelion, that's this red line right here. So we simply have to add A plus C, and that would be 35, and we're dealing with millions of miles, so 35 million miles. That would be that piece right there. Okay, now we're on to our final two questions. Write the equation of the set of points P, X, Y, such that the sum of its distances from 2, -4 and 2, 10 is 18. So a question like this almost seems impossible, but what you have to remember is that if you ever see a question like this is relating to the definition of an ellipse. So what I mean by that is, if you remember from the very beginning of the ellipse unit, or the ellipse like VWs, an ellipse is defined as if you have 2 points that are fixed, your focus. All of these points that generate the ellipse are simply, I'll make it a little nicer, all these points are the sum of the distances. Such that it's constant. So basically, like if I were to pick this point and I were to connect them, this leg plus this leg would be the exact same value as this leg plus this leg. And I can do that everywhere. So that's what it means. So for a question like this, we just have to use that concept and figure out how it's going to be useful. So let's just sketch what we know, and let's see what we can figure out. So 2, -4 and 2, 10. So 1, 2, that's -4. And then we'll say 10's up here. So if it's giving you 2 fixed points like this, those points must actually be the 2 focus points. So we'll put F and F right there. But then it says the sum is 18. So we got to figure out, how do we use that? So to help us, I'm just going to sketch a generic hyperbola, not hyperbola, a generic ellipse here. So something like this. And it says the sum is 18. So this is how we're going to use that information. Let's pick a generic point right about here. Like, let's say it's right on top of the focus. What we know is that this line plus this line must be 18. Now, if I look at it, this is actually interesting because what if I said I grab this and put it right there? This is the same thing, which means that this 18 is the length of the major axis. So the 18 is actually really useful when it gives you that constant, because if it's the length of the major axis, that would mean 2a must equal 18, which then means a must be 9. So we already have a, which is great. Now if we have the focus points, that means we can also find the center. So 2, -4, and 2, 10, the center should be 2, 3. So we can mark that. So already we can actually make a pretty nice equation. We know that it's x minus 2 squared plus y minus 3 squared equals 1. And it's Korn form. A is 9. So already we have that's 81. And look at that, all we need is one more piece. That's pretty good. So the final touch is obviously the formula we always use. C squared equals a squared minus b squared. I know that a is 9, so that's 81 since you square it. B squared is b squared. And this distance, we actually know this, that it should be 7 because it's 3 to -4. So plug that in, that's 49. So b squared should equal 81 minus 49, which is 32. And we stop there because I can plug it in now. B squared is 32. And there's our equation. Now let's go to the final question. This is a pretty cool question. It says the ellipse has this equation, and then Q and C are the endpoints of the major axis, T and M are the endpoints of the minor axis. Find the perimeter of this quadrilateral. This is a great example of like a test level question, because you're going to have to go through quite a few steps. You're going to have to figure out, well, this equation has to be converted into standard conic form, so you complete the square. Then we got to find all the endpoints of the major and minor axis, connect them, and then find the perimeter. So to do that, let's first work with the equation. Let's put the x terms together, put the y terms together. Let's move that -4, and let's complete the square. The y part is nice. I can just add 4 here. The x part, we got to do a little bit of work. We got to factor that out. So put +4. And remember, that's not a 4. That's going to be a +16. I'm going to add 16 there. And now we just keep going. So that's 4x minus 2 squared plus y minus 2 squared equal to 16. Let's divide everything by 16. So x minus 2 squared over 4 plus y minus 2 squared over 16, that should equal 1. Okay, so we got a couple things already. The center is 2, 2, and we can see it's in Korn form. So let's sketch this thing. Let's put that center in, 1, 2, 1, 2. There's our center. Now it says Q and C are the endpoints of the major axis. Actually, let's not use C anymore. We have to use that in our picture. So in the x direction, it goes 2 out. So 1, 2, 1, 2. That's the minor point, so T and M. And then 4 up in each direction from the center. 1, 2, 3, 4. Call that Q. 1, 2, 3, 4. Call that C. And then here's our quadrilateral. So all we gotta do now is figure out what our what is the perimeter? And if it's easier, you can fill in the actual coordinates. That's 0, 2, this is 2, 6, this is 4, 2, and that's 2, -2. What I would do is look at the inside. If I connect these two, my picture is not great, but this is a right triangle since these are all on the same line. And I can see that this is 2 and this is 4, which means this is root 20 by doing the Pythagorean theorem. And if I go further, I'll notice, oh look, if I do this, that's also 4. If I do this, that's also 2. Oops, again, this picture is not fantastic. Make it a little straighter. Make that a little better. Which means all these triangles are the same thing. So the answer is just going to be root 20 times 4, or 2 root 5 times 4, which is 8 root 5. Done.